Okay, we talked about series circuits, and now we're going to talk about parallel circuits. When we were talking about a series circuit, there was only one path that the electrons could flow through. In a parallel circuit, you're going to notice that's different. Okay? So we've got the electrons, they start to move, and they get to a junction. And at this junction, the electrons, right here, when they get there, can either go here or over further. And again, there's another junction. They could go up, or they could go to the last light bulb. So there are actually three different paths the electrons could take in this parallel circuit. Okay? Some differences would be that even if we unscrew one light bulb and remove it, the other two light bulbs will stay on. The reason is they're still connected to the potential difference. Still connected to the negative terminal, still connected to the positive terminal at the top. And the third one as well, connected to the negative terminal along the bottom and the positive terminal along the top. So they're still connected to the potential difference, and therefore the current can still go through. Some other things. Since each light bulb is connected to the potential difference, the potential difference stays the same. Potential difference at each of these is going to be the same. So if we've got a potential difference of 12 volts at the battery, then the potential difference at the first light bulb is 12 volts. At the second light bulb, it's 12 volts. And at the third light bulb, it's 12 volts. However, the current is not going to be the same. Okay? The current is going to depend on the resistance. So let's say that at this light bulb, the resistance is 2 ohms. This light bulb has a resistance of 3 ohms. And this light bulb has a resistance of 4 ohms. The current going through the light bulbs won't be the same. This one has the least amount of resistance, so the current here will be going the fastest. The current here will be going slower, and this will be the slowest because there's the most resistance here. Another big difference is how we calculate the equivalent resistance. Remember, the equivalent resistance is what the resistance of the battery is if you were to combine all of these. Okay? So if you were to take all of these and make them into one big light bulb with a resistance, the resistance would be the equivalent resistance. You look at this equation, we've got 1 over the equivalent resistance is equal to 1 over the resistance of light bulb 1 plus 1 over the resistance of light bulb 2 plus 1 over the resistance of light bulb 3. So we're adding up the inverses, okay? But even when we add up the inverses, what we're trying to find is still the denominator. So when we go to solve that in a problem, we'll get a little more familiar with how to do that. Next one we've got is Kirchhoff's current law. It says the current going into a junction equals the current coming out of the junction. Okay? So current going into this junction right here is going to be the same as the current going out of it. So this current in blue is the same as the current that comes out. And we've got 3 different spots for it to come out. So the current that goes in, which is the current that goes in is the same as the current that's going through the battery here, is going to be equal to the current through the first light bulb plus the current through the second light bulb plus the current through the third light bulb. And if there are more resistors or other components, we could add them in there as well. This is a really good way to check your work. Okay? So when you're done, you find everything. You can check your work by making sure that the current at each of the resistors or light bulbs adds up to the current at the battery.